Record types are a very underused part of C#. They provide you immutable data structures, and by having a really concise syntax, as with our example here, a person with just a couple of properties, this saves you dozens of lines of boilerplate code that it generates for you. But it's really important that you know what boilerplate code does it generate for you behind the scenes. And if you know what that code is and how it works, you can make full use of the record class in the knowledge you're getting the most out of it. So in this little video, I'm going to take you through exactly what code the compiler generates for you. Make sure you stick around to the end. There's an interesting internal method that the compiler generates for you, which allows the support for the with keyword. So let's go ahead and create our own class which simulates the same functionality as this one. So we're going to comment out the record definition, and then we're going to create our own class. Here we go. It's called person. Our person is going to need storage for our two parameters, our name and age. So we're going to create two read-only backing fields. They're read-only because as an immutable data type, of course, we don't want to change them once they're defined. In order to back that up, we need two public properties. Both of them have a public get that simply returns the value of the property. Both of them have an init as the setter. Because it's immutable, it needs to be init in order to ensure that it's been set during construction. Next, we're going to need a constructor. The constructor will take the two positional parameters that we saw defined for our person, and all it does is assign them to our backing fields. So that's all pretty simple standard stuff. Now it gets a bit more interesting. We're going to override toString in order to give a really nice easy piece of feedback when you're using this type. So we're going to use a string builder. We're going to start off with the name of the class, squiggly brackets, and then internally we're going to output the value of our two internal properties. Now we're going to use an internal method. Let me show you why. We're going to call this virtual method, and it's just outputting our two properties, name and age, as values into the string builder. So why do this as a separate virtual method instead of just putting it here in line? Well, it's possible to create a derived class from a record, and so the derived instance would simply override this, output its own new properties, and then call the base class in order to get the base properties. So that supports the ability to have inheritance with a useful implementation. Okay, let's check that what we've done so far works. So we're going to create two instances, John Doe and Jane Doe, and then we'll simply call writeLine. And this should use our toString override to give us a user-friendly output. And there we go. Sure enough, it does as we expected. Now it gets a bit more interesting. We're going to add the ability to do comparisons between instances. We need to add the iEquitable interface, and we'll see that implemented in just a moment. The next thing we need to add is a little helper protected method called equality contract. This is added by the compiler generated code, so I'm just mimicking that, and it returns the type of the person. So this method is a helper that returns the type of this particular record class. Now we need to implement some other basic functionality, get hash code. This is important because we want different instances to have a different hash code so that they're placed inside a dictionary efficiently. So it's going to do, first of all, generate a hash against the equality contract that we just saw. So it's going to hash the name of the type, and then it's also going to work on a hash of the actual name, internal value, and the age. So this will give us a unique value, or at least almost unique value. Okay, so now we can move on to the real meat of this, which is the equals, the comparison capability. The equals with the name of the class is used to satisfy that interface. So the first thing we do, we're going to check if the incoming instance other is identical to the same reference as this instance. If they're both the same instance, you're comparing yourself against yourself, in which case, well, true, of course it is itself. There's a little trick here. Notice we've got object as a cast. If we don't do this, what we'll end up doing is comparing ourselves using a different method later on, which is typed, and that would cause it to go into an infinite loop. You'll see that in a moment where it'll become clearer. If they're not the same instance, then we're going to go on and say, look, if other isn't null, which it has to be, if we compare ourselves as an instance to null, then it's never going to be equal. We're going to make sure that the classes are the same type, just in case the other type is a derived class. So we want to be the same type, and then we're going to do a comparison, equality check for our internal values, name and age. So this will return true if the other isn't null, it's the same type as ours, and it has the same values. Great. Now, this is an override of the built-in equals. Equals comes from the object-based class definition. Really, it's the same thing as the above, except it's not strongly typed. You can see that it has an object type. So we're just going to make use of our existing method. We'll just call onto it by casting person to an object. So that gives us a quick, easy implementation. And now we're basically doing the same thing, except we're going to override operators. We want a comparison operator. We've got ourself and the other are both strongly typed. Again, we used a trick where we cast to an object in order to do a reference comparison. Remember when I said before we were doing that? If I didn't have these casts, then comparing left to right would actually just call back to the same method, because this method is comparison of left to right, and that would cause a stack crash because it would just go around in an infinite loop. As long as we're not the same reference, then actually we're just going to reuse the equals method we've already implemented to check if they are equal or not. Very simple. Finally, the not equal. Not surprisingly, this implementation is trivial. It's just a case of the opposite of it being equal. Okay, so now we've added the equality check-in comparison. Let's add some output code to check it works. We're going to check the two equal methods and the two operator overloads. Let's run that and see how it goes. Okay, so John is not equal to Jane, so false. John is also not equal to Jane using the other equals. Using the equality comparison, of course, false, and not equal is true. So that's given us all the correct answers. Pretty good. Now we can make another quick change. We're going to add a deconstructor. We want the ability to return the name and age using deconstruction, a very simple method, out parameters for the two properties. And then if we just add code to double check that, we'll take John, we'll deconstruct it into two variables and output it. Let's check that works. And sure enough, John deconstructor gives us our name and our age. Now this is where it gets quite interesting, and I discovered something I didn't realize from the decompilation analysis. Now we're going to add a clone method, which, as the name suggests, is just going to create a new copy of itself with the same values. The implementation is going to use a protected constructor, which takes the original and just sets the values. This is the same as the code that's in the decompilation, almost, and I'll show you why once I compile and run this, why there's a little gotcha here. So here we go. If we're going to make a clone of John to make Alice, we'll then output it. Let's compile and try that. And there we go. Alice is a person which has just a copy of the values from John because we didn't change any values. Now what's interesting is that there is no public method clone, as you will know if you have experience of the record class, because in reality the compiler generated code has a dollar after the clone. As a result, it's not publicly available. Now I can't do that with my pretend implementation because it just won't compile, it won't work. So let me show you and prove to you that there is actually a clone in the underlying code. I'm going to comment out my implementation, put back the original record, and then we're going to go down and put some code in here. So we're going to do it the way we really would do it in a proper implementation. We're going to say Jane with, that will create a copy, that will call the internal clone method, and then it will write over the name with the new name. In this case, Alice. We'll then write that out to make sure it works. Then I'm going to prove that the clone dollar actually still exists as an internal method. It's just we can't call it externally. I'm going to do that by going through using reflection on the methods, list out the public methods, and then we'll see the name listed. And that will prove the way that clone actually is used. Whenever you have a with, it actually has two steps. One is to use the clone, and then it assigns each of the properties in your anonymous object here into that clone. Let's run it and check that's the case. So there we go. Look, Alice has indeed worked with the name overridden because of the with clause. If we look at the methods available and go down, there it is, clone, the internal method with a bizarre looking name, and that bizarre looking name stops it being publicly available to us to use, and it's only used internally. So there's a little trick. You now know that the with will use the clone method followed by assigning individual overridden values. I hope you found that useful. If so, hit the like button, and until next time, happy coding.